Washington in Seattle, and I'm going to talk about dynamic optimization in radiotherapy. So thanks a lot for getting up early and coming here at 8 a.m. I know it's hard. So let's get started. So first I'm going to start with some acknowledgements and then get into the actual material. So the first is Min-Sun Kim, who was my doctoral student. She graduated 1 year ago. And this tutorial is basically based on the work that I did with her as a part of her dissertation. So she was a very rare student, hard to find, meaning that her background actually was in physics, and then she was trained as a certified practicing medical physicist, had worked with several hospitals before joining the PhD program at the University of Washington. And actually she ended up getting a PhD working with me in applied mathematics. So that was a very rare combination of expertise that she had, and that I think benefited, the research benefited quite a lot from that combination, I think. And my second acknowledgement is actually to Professor Mark Phillips, and the main reason is that he actually introduced me to Min-Sun. So this could not have happened without him. And then later on, as he started working on his research, because he is basically working at the hospital in the University of Washington, we did talk to him about some of the ideas that we had, and kind of he always brought us back to the real world when we did crazy things, basically that were not really practical in some sense. So that's important. And then it's kind of funny that Professor Edwin Romain actually was instrumental in me meeting Mark Phillips, meaning that Edwin actually came to give a talk in my department in Seattle, and I went to that talk, and Mark Phillips was in the audience there, and then the three of us had coffee basically, and that's how I kind of started thinking about this area of radiotherapy. So if we had not had that coffee, this would not have happened. So that's a big debt to Edwin. And then to Marina Appelman, who is actually here. So one time actually I gave a talk, a short talk based on some of this work, and at the end of the talk, I don't know if she remembers, but she winked at me and she said, "This is neat." Okay. So because I was at that time completely new to this area, so I was not sure what I was doing. And then I went back home and I was talking to Min-Sun, and actually some of the ideas Min-Sun said, "This is junk, basically we should not do this." And then I said, Marina said it was neat, so we are going to work on this at least for a little while and then see where it takes us. And then this is how this research kind of started. So that's why I'm indebted to Marina also, so thanks for that. So in fact, recently Informs invited me to blog about this topic, my work in this topic, on a blog that they have started recently. So if you want to read a story about these kinds of things that I just mentioned, you can go to that blog and find this topic there also. And then last but not the least, National Science Foundation. So some of my current research in this area is actually funded by a grant from them. So that's why I'm acknowledging them as well. So let me get started. So I'm assuming that people here basically don't really have background in radiation therapy. So I'm going to start out with some basics, not spend too much time, but at least talk about it enough such that everybody is on the same page when I use certain words or terminology or notation later on in my talk. So some basic background in radiation therapy. So millions of people have cancer and will continue to have cancer all over the world. So World Cancer Report 2008 predicts these two numbers, so 17 million and 75 million. In the US, I believe cancer is the second leading cause of death. I believe second only to heart disease. So in the US also a lot of people do have cancer. And in the US, about half of people who have cancer actually receive some kind of radiation therapy. So as you know, there are different ways in which you can treat cancer. For example, chemotherapy, surgery, radiation therapy. So about half of them actually receive some form of radiation therapy. So all this stuff, you can read that from the National Cancer Institute website. So the talk today actually is going to focus on one particular kind of radiation therapy, which is external beam radiation therapy. And as the name suggests, you can guess that that basically means that the beam, so radiation beam, is going to come from outside the patient's body. So that's what external beam means. And this is a picture I found on, again, National Cancer Institute website that basically shows, the basic setup of how this works. So there is a couch on which the patient is actually there, and there is a machine which basically is connected to a linear accelerator. It's called a gantry, which can rotate and pass radiation through the patient's body. Okay, so that's the idea in external beam radiation therapy. So that's the basic setup. So what are some of the key issues in radiation therapy? So I think most of you know this, but the idea is that radiation is going to kill tumor cells, and that's good. But unfortunately, it's also going to kill healthy cells that are right next to the tumor cells, for example. Okay, so that's a big problem. And therefore, the goal in general is to maximize essentially some kind of a differential between how much tumor you kill and how much damage you actually do to the healthy cells. That makes sense, right? So that's the key high-level idea in radiation therapy, and in particular external beam radiation therapy. So the way this typically works at a high level, conceptually at least, is that you have to plan treatment for a patient, and you can start off by taking an image, so CT scan or an MRI scan, and the image will basically show you roughly where the tumor is in relation to the patient anatomy, so other parts of the patient's body. And this is something I found on Google. So this is, I believe, an MRI scan of prostate cancer, and the arrows basically kind of delineate a darker gray portion, which is basically the cancerous region. Okay, so that's how you can kind of see cancer or tumor in an image, which is an anatomical image. And I am kind of emphasizing this word anatomical here because later on in the talk I am actually going to talk about something called biological images, which are going to be different from these kinds of images. And when you see the picture that I show you later on, you will notice the difference. Okay, so keep this picture in mind, and you can contrast that later with something else that I'm going to show you. So once you have an idea about where the tumor is in relation to the patient's anatomy or other parts of the body, the way this goal is kind of the goal of maximizing the differential, the goal kind of is attempted. So to reach that goal, what people do is follow two-pronged approach. So basically try to do two different things to reach that goal. And the first is called spatial localization of dose. And as the name suggests, this has to do with space. Okay. And the second is temporal dispersion of dose. So the second, of course, has to do with time. Okay. So on this two-pronged approach, the idea is that, so in the first, so it's bullet A, spatial localization. So the idea is that you give more radiation to the cancerous tumor as compared to the healthy cells. Okay, so you somehow manage that. So you design your treatment such that the dose, so in this context, dose means energy per unit mass, and the unit for that is gray. So the dose is localized, or it conforms to the shape of the tumor. Okay, so that's the high-level idea. So that's spatial localization. And temporal dispersion, and I'll talk about these two in detail, basically relates to the fact that you're actually not going to give the entire treatment in one shot, but you're going to give it over time, okay, in smaller portions, essentially. Okay, so that relates to temporal dispersion. And we'll see why that is done after a few minutes in the talk today. Okay, so I'm going to talk about spatial localization for a little bit, just as background, some basic high-level concepts, and then go on to temporal dispersion. So spatial localization, this is just a simple picture that I drew to give you intuition behind the key idea here. So the picture shows a boomerang-shaped tumor, and the letters OAR stand for organ at risk. Okay, so that's basically healthy anatomy in the patient's body. I'm going to use different kind of names for OAR, so I just interchangeably use words like normal tissue or healthy tissue, healthy cells, normal structure, organ at risk, all these things I'm going to use interchangeably. But basically that is something that will be damaged if too much radiation is given to that. Okay, so that's something that you want to protect, and tumor is something that you want to kill. So the idea in spatial localization, as you can see in this picture, is that you do something called intensity modulated radiation therapy, which basically means that you're going to modulate the intensity of your radiation field or radiation beam as shown in the picture. So what I'm trying to show there is that the intensity, so the arrow goes up so high that way. So as you can see, the idea is that you have a dip in your intensity profile near the OAR, near the organ at risk, right? So you want to give very high intensity to the tumor and low intensity to the OAR. Making sense, right? So that the OAR will be protected. So that's what is shown in the picture. So that's the basic idea in intensity modulated radiation therapy. So I'm giving, as you can see, go here, high radiation here and high radiation there, and I'm trying to avoid giving too much radiation here, okay, because there is that organ at risk. If you want more concrete example of where this can actually happen, so something like this can actually happen in head and neck tumor, where the tumor is wrapped around your neck like this, for example, and you can think of this as your spinal cord looking from top, okay? The reason I did not draw a circle, because it was hard to fit the 3 letters OAR in that circle, okay? But it's easier to imagine a circle for spinal cord looking from top, okay? So that's the idea. And then, so how is this done? So how do you actually modulate this intensity profile? And that is done by something called a multi-leaf collimator. So this is basically a bunch of leaves that can move like this, as shown by the direction of the different arrows, the 2 arrows. And basically, the radiation is going to come from here, for example, right? So this is an opening in my machine, so in my gantry, if I go back, this is going to be somewhere over here, right? And radiation is going to come from top, right? And the idea is that the leaves that you have, so these leaves are going to move such that you shape the beam appropriately, so that, right, it conforms, so the radiation that you give conforms to the shape of the tumor. That's the idea, basically, and that can be done using this collimator, for instance, okay? So that's the basic technology in IMRT. And then this picture actually gives you some intuition behind why people actually use multiple beam directions rather than just one direction while giving treatment. So this is just something that I drew. So again, I'm trying to show, you know, the head and neck kind of example that I gave you. So this is that tumor wrapped around, if you want. Think of this as the spinal cord, so organ at risk, something that you want to protect, not damage too much. So the idea is that if you look at the top beam, top field, you would want to have this kind of a radiation profile for that, intensity profile for that. And the reason is, just like in my earlier picture, you don't want to pass too much radiation through this part, right? So that's why there is the dip there. But the bad thing about that dip is that you will actually end up giving less dose than you want to this part of the tumor. Makes sense? Because there is that low intensity portion there. And that is called a cold spot, just not enough radiation to kill tumor. So the idea is that to avoid something like that, you're actually using multiple directions, so beam from multiple directions. So this is another beam, and as you can see, I'm actually using high radiation here. So the hope is that, you know, this will compensate for this cold spot, essentially. Okay, so whatever was, you know, kind of lacking, this will make up for that. And of course, I have to have a dip here as well, because I don't want to have a high intensity here to protect this OAR. Okay, right? And the same idea with that beam as well. So that's basically why you would use multiple beams, and that kind of depends on the geometry of the tumor in relation to your organs at risk. So for something like this, you know, this concave kind of geometry with an OAR that is hidden inside, multiple beams will actually make sense. Okay. So any questions so far? Okay. Okay. So that's the basic idea. The way treatment is planned is by doing something called fluence map optimization. So fluence map is basically the radiation intensity profile. So this is actually called inverse treatment planning. It is called inverse for the following reason. So you actually start off by specifying a treatment protocol, and a doctor can do this. That is based on empirical, so clinical evidence and experience and other guidelines and so on. But basically you start off with a protocol that prescribes, let us say, a uniformly high dose called prescription dose, so deep risk, to the cancerous target, so the general tumor area. and basically set some kind of a tolerance limit, and I'm going to call that D tol for tolerance. So limit on the OAR dose. Okay. So the idea is that I want to give, so ideally speaking, I want to give as much dose as possible really to the tumor without giving too much dose to the organ at risk. That's the rough idea at a high level. But here, there is a prescription dose, so the doctor is saying that, okay, give this dose to tumor and don't give more than D tol to the OAR. So that's one example of a simple, really the simplest protocol probably. And then if you start thinking about how actually you do this, in mathematical models of these kinds of problems, each beam is actually discretized into smaller segments called beamlets, and the patient's body, tumor region, other anatomy nearby is discretized into something called voxels. So voxel is just like a pixel, but three-dimensional, so three-dimensional cubes, you can think of them like that. So that's done in mathematical models. And then the beamlet intensity, so these small portions of the beams, so the intensities there are actually optimized to obtain a dose distribution that is as close as possible to the prescription, right? So doctor is saying do this, perfectly achieving that may not be possible, so you're trying to do as close as possible to that, okay? So that's how kind of optimization comes into play, because you're trying to do something as close as possible to this prescription. And this is basically, you can think of this as a basic fluence map optimization problem. Okay? So what I will do is actually, just to get started, I'll give you a very simple example of a fluence map problem. This was one of the very first models that I think was formulated in the mid-90s, I believe. So let me give you some basic notation. So this is a tutorial as opposed to a 20-minute talk. So I'm going to have some math here with notation and so on. Much more detailed than a typical 20-minute talk. Okay, so I'm going to start with some basic notation. So remember I talked about voxels, so small 3D cubes in the patient's body. So let's say that we have n tumor voxels, m OAR voxels, k beamlets, and let's use the letter U throughout this talk to represent intensities. So I'm going to have an intensity vector U. Intensities have to be non-negative, so that intensity vector is in R plus k dimensional because I have k beamlets. Make sense? So that's the basic notation, three things. And then think about it, if you want to plan treatment, if you want to start thinking about formulating an optimization problem, what you will need is somehow you need to figure out, if I use these intensities, right, how much dose will actually be delivered to the patient, right? Different parts of the patient's body. So how much dose will go to that corner of the tumor versus how much dose will go to that corner of the organ at risk, right? So you want something that transforms the intensities into dose, which is energy per unit mass, okay? And that's called a dose deposition matrix. So the transformation is going to be linear basically. So A is the letter I'm going to use for my dose deposition matrix, and the matrix is basically n plus m times k. Okay, so it's going to have k columns, n plus m rows, and the idea is that I take this A, multiply my U, which is the intensity vector, with this A, right, and what I get will be the dose. Okay, and so I'm going to use letter tau throughout this talk to represent things that have to do with tumor, and the letter phi to represent things that have anything to do with the OAR or normal tissue. So basically, if you want to think about what dose will be given to the ith tumor voxel, it's going to be my tumor dose deposition matrix times my intensity vector. So I do that product and pick up the ith component of that. Okay, so that will give me the dose that is deposited to the ith little cube inside my tumor. Okay, so that's the idea. And then you can imagine exact same thing will be true for that A phi, which is my OAR dose deposition matrix. So I multiply that with U and take the jth component to figure out how much dose will be delivered to the jth OAR voxel. Okay, so that's basic terminology that I will use again and again throughout this talk in different contexts. So let's go back to what I had said a minute ago. So remember I had said, you know, the basic idea is to somehow figure out, you know, an optimal intensity vector such that what is delivered to the patient will be as close as possible to the prescription. Okay, so I'm going to write down a very simple optimization formulation for that problem. So what I'm going to do is I'm going to minimize deviation of the tumor dose from the prescription dose that the doctor told me, right? And I'm going to penalize anything to the OIR that is above the tolerance limit, right? Yeah.
Do you worry about like discretization errors on the boundary? So some voxels are going to be both.
I guess, sure, in some sense. I think the voxels are very small, like 5 millimeter by 5 millimeter, or 1 centimeter by 1 centimeter. But there will be small errors, I guess. Is that?
Well, correct me, but I think you do identification of tissue, or at least you could do identification of tissue before you do the discretization. But so you know, in some cases, it's not a discretization error. Some voxels, if you have lung cancer, some voxels are cancerous, but they're part of the lung. So.
So, and that formulation for that would look like this. So here what I'm doing is, like I said, I'm going to minimize actually square deviation. So this, as I said, is the dose to the ith tumor voxel. So I'm subtracting the prescription from that square, and I'm summing up over all tumor voxels. That's the square deviation sum. I'll talk about these things in a minute. So let's ignore that for now and go here. This is similar. So again, I'm calculating the deviation again. So the dose to the OIR jth voxel, subtracting the tolerance dose. The only difference is that I'm putting a plus sign here, and what that is going to do is basically it's going to take the maximum of this number and 0, okay, and then square that. And the intuition behind that is that I only want to penalize things that are above dtol, but I don't want to penalize things that are below. Okay, so that's the idea, and I sum again over all OIR voxels. This N and M, remember N tumor voxels, M OIR voxels, so these are just normalizations basically, and these are weights, so we can think of these as importance weights. In some sense this is a multi-objective problem, so you can think of those as importance weights being attached to the tumor versus the OIR. Okay, so that's one of the I think early models for this fluence map optimization. And then since mid to late 90s, millions and millions of different models have actually come out, I believe. Different kinds of treatment protocols. When you have a different treatment protocol, your model will correspondingly change, right? Then your algorithm for solving that might change, and so on. So these are some of the surveys that I found that talk about different protocols and the corresponding different models. Okay, so you can take a look at those later if you want. One thing I want to mention is something called dose volume protocol, which is commonly used. So that says something like not more than 30% of the organ at risk should receive more than a certain amount of dose. Okay, so that's a dose volume protocol. And typically I believe that is a model using some kind of a mixed integer programming formulation that makes the problem difficult to solve. But that's one thing that is not a part of what I showed you earlier. What people have also done, and I'll briefly touch upon this later on, is that remember I mentioned uniformly high dose in my protocol for the tumor. People have used non-uniform protocols based on some more sophisticated images called biological images, and I'll talk about that a little bit later on because those kinds of images are going to be relevant for the rest of my talk later on anyway. Okay, so basically lots of different kinds of formulations of these spatial localization problems. Yeah.
In your objective function, is there a difference between using absolute value as objective function?
Absolute value where?
Absolute value of the deviation.
Yes, that could be done, right? And in fact, you can formulate that as a linear program also. If you have absolute values. Yeah, this is really just one example. Like I said, there are millions out there. But you're right, I could use other things as well. In fact, sometimes some of these things can even go into the constraints, right, where I put that as a hard constraint instead of doing something like this and so on, right? Okay, so that's about spatial localization. So the second component is actually temporal dispersion of dose. So let me talk a little bit about that. So as I said before briefly, this radiotherapy is basically administered daily over several weeks, so let's say 5 to 9 weeks. So the patient comes back again and again, and a little bit of the dose is actually given every time. And one of the reasons for this is that healthy cells actually have better ability to recover from damage than tumors. So the idea is that if you give 8 to 12 hours between 2 treatment sessions, by the time the patient comes back, whatever damage was done to the healthy cells, they would have actually recovered from that. Okay, so that's one of the reasons you actually do this temporal dispersion. So rather than giving the whole thing one shot, you actually give it over several weeks. Okay. I also want to talk about this picture that I drew in this context, because this picture will actually become important later on in my talk. So this picture basically shows conceptually something called a cell survival curve or normal tissue damage curve. Those are equivalent. So let's just look at this. So the x-axis here is dose. So dose increases this way, okay? And the y-axis is normal tissue or OAR damage. So that increases that way, right? So more damage here as compared to up top there, okay? And so first you should look at the red line, which is this line. So basically this says that if I give, let's say, this much dose in one treatment session, this much damage will be done to the OAR. Okay, that's how you can think of this picture. So that's the first red curve. What I'm trying to show here is that what happens if you actually break the dose into smaller portions, right? So 2 or 3 portions, let us say. 3 portions, I believe, in this picture, and then give that. So I'm trying to show 2 kinds of things in this picture, using the green part of the picture and the blue part of the picture. So if you look at the green part, you can see that because this dotted line is vertical, right, the dose that I'm giving is actually the same as this D1, right? However, you can see that the damage that is done is significantly less, right? And that's because that same amount of dose D1 is actually broken into smaller portions, and these are actually called fractions. Okay, and I'll talk about that more later on. So that's one way to look at that. The other dual way to look at this is that, again, if I again broke my dose into smaller fractions, so 3 fractions, you can see that I can give much more dose, which I'm calling D2, for the same amount of damage to the organ at risk. Okay, so that's the dual of that earlier situation, and that's important because I want to give as much as possible, really, in some sense, right? Because the more the dose to the tumor, the better it will be, right? So that's why the dual part is also important. Okay, yeah.
So why don't you assume the tumor cells are equally good at recovering?
Equally good at recovering. I think that the reason is I've just read this in radiobiology books. So just because tumor cells, I guess, behave differently from normal healthy cells, that's the reason, basically. Okay. But I don't know more than that. I'm not a biologist. But that's, I think, correct. Okay. So that's this picture. I will come back to this picture again later on, but I think the basic idea is clear from the picture. And in fact, I will actually use a particular functional form later on to represent this curve that I drew here. Okay, and I'll talk about that when I get there. So that's the idea in this temporal dispersion. So the way this is typically done is that you first solve a fluence map optimization problem, which will give you intensities, right, and a dose distribution basically, and then you kind of break that total dose up into a series of typically equal dose fractions, okay, or treatment sessions, and then deliver that. Okay. So for example, people say this treatment is 2 gray per fraction for 15 fractions, or 1.5 gray per fraction for 20 fractions, or something like that. So that's the most typical. There have been some variations of that, of course, but that's common. Okay. So now let's start getting closer to actually my work, so our work. So what are the limitations of some of these things that I talked about? So you can kind of guess what those are. But in radiobiology, actually, there are something called 4 R's of radiobiology, and so this is a Bible of radiobiology. This is where I learned what little I know about radiobiology. But that book basically says that so repair of sublethal damage in normal tissue. So basically cell repair in normal tissue. So that's the first R. Redistribution of tumor cells into radiosensitive phases. So cells life cycle. Okay, different phases of that life cycle are different in terms of radiosensitivity. Okay, so tumor might be more radiosensitive in one phase of the cycle as compared to another. Okay, so in a sense, what you want to do is really catch the tumor in the most radiosensitive phase of the life cycle, so that you will be able to kill the tumor with the least amount of dose, in some sense, right? So that's the second R, and the third R is actually reoxygenation. So oxygen content near the tumor actually becomes important in determining efficacy of treatment, because if you have low oxygen, okay, near the tumor, that actually makes the tumor less radiosensitive, okay, and that's called hypoxia. And there was a talk, in fact, yesterday about that in the evening session, and I will talk about that a little bit later on also. But so oxygen content near the tumor is also important, so that's the third R. And then repopulation, so tumor cells grow and so on, so that's the fourth R. So these four things basically are going to determine the treatment efficacy. And as you can see, these are extremely complex biological processes that we don't really understand completely. People have tried and people are trying, so our understanding of this is improving, but these are still complex. And because of essentially insufficient information, there is a lot of uncertainty in how and whether we can model these things, okay? So what state-of-the-art optimization models do, I just showed you very basic models, but essentially all variations of those models, or almost all variations of those models, I believe decouple the space component, so the spatial component of the problem, with the temporal component of the problem. In the sense that, like I said, you first solve the spatial component of the problem and then break it up into equal dose fractions. Okay, so you're essentially, in some sense, decoupling the two. And in a sense, you're ignoring uncertainty in response, so tumor response, so how tumor will actually respond to treatment, how these things will progress, right, in response to radiation treatment, and the uncertainty in that is being ignored. And because of that, the treatment is not really adaptive to how the tumor is responding, or how these biological processes are happening over the course of the 5 to 9 week treatment. Okay, so in that sense, the state-of-the-art models are not adaptive. Okay, so let's keep these three things in mind. And the way I view this is actually one size fits all. Remember, I said 2 gray per fraction for 20 fractions, right? So you give that to a particular kind of tumor. Okay, so let's say head and neck tumor or something like that. So I kind of personally view that as one size fits all, or in other words, a static deterministic view of radiotherapy, right? Static deterministic meaning, like I said, I'm ignoring uncertainty and I'm solving a problem at the beginning. So one shot, I'm solving a problem and then breaking the dose up into several fractions, right? So that's a static way, in my view, of thinking about this problem, okay? So can this be changed, or is this changing? And the answer to that is actually yes. And there are two things that are at the heart of why that is happening. So the biggest issue, or the biggest contributing factor to that change, is technological improvements, basically. So there is something called biological imaging. So because of biological images, you can actually understand a lot more about the tumor's behavior these days than you could a while ago. So these are names that I found in different books and papers and so on. So FDG PET, so positron emission technology, that's PET, and FDG is basically a fluorine tracer or tracer, or choline citrate MRSI, so magnetic resonance spectroscopic imaging. Choline citrate is again another tracer. So these things can be used to track cell density, and I actually have a picture, I believe, of that I found on Google. So this is in contrast with, remember the earlier picture that I showed you was kind of similar to this, that was MRI, which was an anatomical image, but this is MRSI with a choline citrate, I guess, tracer, which basically in some sense tells you how much tumor density is there in different parts of the tumor, okay? And it is quantitative, meaning that these colors, so blue means low, red means high, but in this picture that I found on Google, there is also this scale that goes with it, meaning that for every color I have a number that goes with it. So there is a 4 point something here versus a 0.01 there. Okay, so this is a quantitative information that I can get from this image about where the high density of the tumor is versus low density. So that's one example. FDG PET also does something similar. I have other examples here. So now there is another kind of image with an iodine tracer, which can tell you the rate at which the tumor is proliferating, right? So the tumor is growing in a particular region. I mentioned hypoxia. I also mentioned another talk yesterday. So hypoxia means hypo-oxygen, so less oxygen, so lack of oxygen near the tumor. So you can actually see where that is in this kind of a biological image. And this is another thing I found on Google. So this is actually this yellow thing here. It basically lights up, okay? So the image lights up in some sense where there is hypoxia, so less oxygen in this portion. So how intuitively, how can I use this kind of an, this kind of an image? Of course, because I know that there is less oxygen here, I will somehow try to come up with a dose prescription, for instance, that gives higher prescription dose to this region of the tumor, right? Perhaps as compared to other regions of the tumor, right? And of course, you don't want to give a very high prescription everywhere because that might be too harmful to the OR, right? So that's called dose painting. And this also is, from the same place in Google. Basically, it's trying to show that I can, so these are red circles, so isodose curves. So I'm giving basically a very high radiation in the place where I'm seeing hypoxia. Okay, did you have a question?
Yeah, so how stable is that hypoxia?
Hypoxia is...
So if I take a PET scan and I see whatever
yeah, whatever the
is,
name is, yeah.
Yeah, and you see that yellow spot, is it presumably going to be there for
No,
a while?
it's very unstable. In fact, it's very dynamic, in fact. So this...
So what kind of time are we talking about?
So it can change. So over the course of the treatment, this does actually change. So as you will see, my research and what I'm going to try and do is somehow try to model how this may change or use what other people may have done in radiobiology as to how this will change and incorporate that into my model so that I can treat dynamically accordingly. Right? Okay.
Excuse me, I think the PET identified is not hypoxia. It's FDG to identify most metabolic activities.
Right, I mean, with different kinds of tracers, I think you can identify different things. So this particular tracer, I believe, can identify hypoxia.
It's actually showing the most cancer metabolic activity area.
Most metabolic activity? Okay. Yeah, I think this is a picture that talked about hypoxia, though I mean, this is not something I wrote, this is something I found. So I'm not an imaging expert, but there are images out there which will show you where there is higher levels of hypoxia versus lower levels of hypoxia or different proliferation rates or metabolic activity and so on, okay, using different kinds of tracers. And I think you also had a similar picture in your talk yesterday for hypoxia. Yeah, so this is dynamic, but this is just one picture, so one shot. Okay. So that's one part of the two pieces on this slide, so biological imaging and tumor response models. So the second part is that tumor response models are also becoming kind of sophisticated. So the most classic, so the most well-known one is log linear quadratic, and that's also in that book that I mentioned earlier, and I will talk about that in that model in detail later on. But there are other more sophisticated models that I also found. So there are birth-death process models of tumors. So basically you model the tumor's behavior as a birth and death process for how the cells are going to die and there's cell birth and so on. There are also heat equation types of models. So Julie Swanson is actually at University of Washington and heat equation. So basically that is a diffusion equation which talks about how the tumor will actually grow, okay, in the patient's body. So that's another so it's basically a different partial differential equation. So those kinds of models are also becoming available. So the idea is, are there benefits to potentially adapting treatment to information that you can obtain from these kinds of images over several weeks of treatment? So perhaps by taking multiple images over the 50 days of treatment, for instance, right, rather than just one. And can you combine those things also with mathematical models of tumor response? And there is clinical work in this area, so people are doing this clinically a little bit. So here are some papers where there are clinical examples of how people have taken these images and tried to use information in these images to come up with treatment plans, okay, that can change over time, for instance, so somewhat adaptive. And in fact, many believe, so this is a paper in medical physics, so many doctors and others believe that this will be actually not only feasible, but in fact common in the future, okay, so use of models along with more sophisticated, advanced imaging to come up with adaptive treatment plans will actually be common in the future. So there is something called a 2020 vision for radiotherapy, so what's going to happen over the next 20 years and so on. So there are papers like that where people talk about this being a possibility, okay. So the ultimate goal, I think in my view, would be to come up with adaptive and completely individualized radiotherapy. So right now, the way I think about these problems is, the idea is to deliver the right amount of dose at the right place, right? So all the pictures, everything I talked about is right amount of dose at the right location. But I think the goal would be that you could add at the right time to this, okay? So the right amount of dose at the right place at the right time, okay? So that could be an ultimate goal, and that is something I would view as individualized radiotherapy, right? Really tailored to what is happening inside the patient's body over time. And I am not a biologist, so as an operations research person, my research question or my interest is really, can I come up with some kind of stochastic dynamic optimization models that can start thinking about in the future getting here, okay? So as I said, the models that are more common are static deterministic. So my research question is actually, can I make, can I build dynamic stochastic optimization models that will eventually perhaps help us get here, okay? We are a long way from there, but in my tutorial today I'm going to show you some basic simple models that we have built to start thinking about doing that, okay? So is the overall idea, overall framework roughly clear as to where the field is and where I'm trying to go with these toy models that I'm going to show you today. Okay, so I'm going to show you two attempts that we did for building dynamic stochastic models. Okay, so the first attempt is just 1 or 2 slides, there is not much in it. So that will be slide 18. So the rest of the talk is about the second attempt that we did at building these kinds of stochastic dynamic models. Okay, so the first attempt, we said, okay, so let's step back and make this as simple, as toy as possible. Okay, so at the heart of this, what is there at the heart of this? You basically somehow, so operations research people, you basically somehow want to, let's think about it this way, take a picture, okay, get the information that is there in the picture, right? Have some kind of a model that will tell me how the next picture will be, essentially, right? Some kind of a probabilistic model, right? And then keep doing that over the course of the treatment and somehow build some kind of an optimization model that will optimize my treatment or treatment efficacy, right? Using this basic, very simple idea, okay? So we tried to do that. So we built the easiest possible, the simplest possible prototype that we could build, which had only these 2 features essentially. So basically a finite horizon problem. Okay, finite horizon because typically the treatment will be 30 days, right? Patient will come back 30 times. So finite horizon problem. You're all in operations research, so stochastic dynamic program, right? So very simple stochastic dynamic program where we will have only 2 things. So we'll have states that relate to the condition of the tumor and the condition of the organ at risk. Okay, so at a very high abstract level, I'm going to take a picture that tells me the condition of the tumor, the condition of the organ at risk, right? And I'm going to have some kind of a probabilistic model for how this condition is going to evolve over time, right? I'm going to use that to build a stochastic dynamic program, okay? And in that really simple stochastic dynamic program, I'm going to have a very simple decision variable, and I'm going to call that prescription dose, and I'm going to only allow for 2 values, high or low. Okay, so very high dose or very, let's say, low dose. Okay, and the probabilistic model, as you can imagine, is going to depend on the dose, right? So if I give high dose, right, the image will change probabilistically in a certain way, versus if I give a low dose, the image will change or the condition will change probabilistically in a certain different way, right? So that's going to be my really simple prototype. And this is the idea basically, this is, I'm showing one fraction here, so one treatment session, observe conditions of OAR and tumors through biological or functional imaging, right? Give your dose. The system will evolve probabilistically, right, to different states, this state with certain probability, this state with certain probability, and so on. And keep doing this, right? And use this idea to somehow build a simple stochastic dynamic program, okay? So that was our first paper, and I was actually in a sense surprised that this paper was accepted, because this is not practical, okay? This is really simple. And this was actually accepted in a medicine journal, so physics in medicine and biology. And I think the reason was that I think the idea was interesting because I had not seen stochastic dynamic programs for this kind of a context before, okay? In particular, in this really simple prototype, there was no fluence map optimization whatsoever, okay? Meaning that essentially you can think about it like this: I'm still actually decoupling the temporal and the spatial component of the problem in some sense, but I'm still trying to incorporate uncertainty. So why am I decoupling the two? What I'm thinking about, and we actually did not do this in the paper, but we wrote it in the text of the paper, that the idea could be that I use this low or high dose, right, as my prescription dose and resolve a fluence map optimization problem in every treatment session, right, in the most extreme case, right? So in that sense, we still kind of decoupled the two, okay, but did try to incorporate uncertainty, okay? And then I'm not going to show you the details of that particular paper. I'm going to show you the second attempt, but I'm going to only show you one picture, and that is actually this picture. So in the paper, what we did was a really simple model where I said, okay, let's have an ordered set of states for my tumor. Ordered meaning I can draw a picture like this, where on this left corner there is less tumor kill, and on the right corner there is high tumor kill, right? So think about it as most of the tumor is dead here, right? Versus none of the tumor is dead there. Make sense? So I can order states like that, and that is actually not uncommon in medicine. Okay, there are other papers by Andrew Schaefer's group and other groups where they talk about ordered health states and use that in the context of stochastic dynamic programs. Okay, it's only that this was used, as far as I know, for the first time in the radiotherapy context. Okay, so that's the x-axis, and the same idea for my y-axis. And this picture just gives you some basic intuition about the structure of the optimal policy that we observed in our paper. And let's see why this is intuitive. So remember, I had only two dose levels, high or low, right? So the dose is high in this region. So there is a region where the dose is high, and there is an envelope like this one, and then there is a region where the dose is low. Okay? And that is intuitive. Why? Because if you take any fixed level of OAR damage, right? So let's say this level, right? The dose is high, high, high. Once you cross a certain threshold, right? Sufficient tumor has already been killed, right? Because the tumor cell kill is higher this way. So sufficient tumor has already been killed. So then there is no point in giving high dose anymore, because you are in some sense unnecessarily damaging the OAR, right? So the dose actually drops after that threshold to a low value. Make sense? Going that way. And the same idea you can think of it going this way, because if you're going this way, the tumor cell kill is constant, right? But OAR damage increases. So once you cross a threshold, you don't want to give high dose. So the dose actually drops after that threshold. Okay? So that's basically the structure of the optimal policy that we empirically observed, empirically meaning in the examples that we constructed. Okay? None of this is treating real patients or anything like that, but the examples that we constructed. We have tried hard to prove, right, that this is actually optimal, okay? But we have been unsuccessful. So if you are interested, please take a look at my paper and see if there is a way to prove that this kind of a structure will be optimal. Okay, there are standard ways for doing these proofs, but the proof is not working. Okay, that's a very interesting problem, I think. But okay, there is a question, I think. Yeah.
How many states do you assume for tumor?
Yeah, so we don't need to assume a number. The only thing we assumed that it was finite, so discretized, so some finite integer interval. Basically, that's all we assume. And that finiteness is just so that my stochastic dB, right, is tractable and so on. Yeah. In fact, so in my second attempt, right, so the remainder of the talk, my state space is actually going to become continuous. So how many, the answer is actually uncountable. Okay, but this very simple first prototype, it was finite. Okay. So that's my first attempt, and this is a 2009 paper. If you want it, I can give it to you, or you can easily find it. It's in PMB. So let's actually go to what we really, or try going closer or to what we really want to do. We don't want to decouple the two problems, right? So we want to do the whole thing together, and that's our second attempt. So let's look at that. So the idea here is basically I'm just showing simple picture here. So I have the gray region L shape as my tumor. The green, the blue square is actually my organette risk, so that's my OAR. And the yellow shapes that I'm showing basically relate to what density I have in the tumor. Okay, so for example here, so yellow shapes, tumor density levels. I'm imagining in my mind in this picture some kind of a biological image, right, that will tell me what density I have, something like MRSI, for example, the choline citrate ratio that I showed earlier. But the disk is high density, triangle is medium density, and so on. Okay. So the idea here is that you start the treatment. So you take this picture that shows you where the highest density is. That's my disk, and then I have a star, which is my low density. What I'm trying to do is, in my mind, I'm trying to build again something like a stochastic dynamic program or a stochastic control problem, where this picture tells me the state of this system, right? And then I decide my treatment. So that's my treatment. So you can see the length of the arrows. Length of the arrows, they basically tell me what the intensities are. So long arrow is high intensity, and so on. So if you think about it, these two, so the northwest corner, so that's that at the top, and this, okay, so those two are basically identical, right? So if I did not have the biological image, there is perfect symmetry between the two, okay? However, because I have the biological image, and because it is telling me that the density is actually higher in the disk versus the star, I am actually using arrows of different lengths. Make sense? So that's kind of, I have that fluence map optimization problem in my mind there, so I'm using shorter arrow there. And that is good. Why is that good? Because that is, so the OAR is in direct beam's eye view of those two, right? So I don't want to give unnecessary dose or high intensity in that region. So then, I mean, I don't need to talk about the whole thing, but the idea is that you do something like this so that you can use the information that you're getting dynamically over time to adapt your treatment plans, okay? One important point that actually I think kind of gets lost in this picture is that this whole thing is interconnected, right? Meaning that I don't want to just take one picture and solve one problem that ends after that one period, and then take another picture and solve a new problem, which is a one period problem, and then roll forward like that. That would be a simple way to solve this, right? Or kind of heuristic to solve this. But that's not really what I want to do. I want to completely integrate this whole thing so that I have some kind of a stochastic control, stochastic dynamic programming problem, right? Which has this temporal as well as spatial component embedded in it, okay? So that's the high level idea. And this is just intuitive idea that we had. So from here, to remember the red big goal that I showed you, adaptive individualized radiotherapy. So we are really far from that, but what we have started doing is we have started formalizing this in a finite horizon stochastic control formulation, right? Starting to build at least some model that actually does this and solves some kind of a problem dynamically over time. Okay, so that's our second paper in this area. And this is actually in an OR type of journal, so European Journal of Operations Research has an issue on healthcare, that's where that paper is. So we call that dynamic biologically conformal radiation therapy. We have also called that adaptive biologically conformal radiation therapy. I think adaptive is more interesting than just the word dynamic. We have called it both, but in the paper we call it dynamic biologically conformal radiation therapy. Why do we call it dynamic biologically conformal? Because in our minds we have this idea that we are going to use biological images, right? And we are going to come up with plans that conform to how these biological processes evolve over time, right? Rather than just conforming to the shape of the tumor, for instance, right? So biologically conformal as opposed to physically conformal. Okay, so that's the distinction we are basically trying to make in there. Okay, so now I'm going to start building models. In next roughly 35 to 40 minutes, I'll show you some stochastic control formulations and some simple heuristic ways to solve those problems. Okay, so the basic framework, as I said, is tumor plus OAR. I'm going to view that as a stochastic dynamic system. As I said before, the states will basically something that tracks the spatial map of how this information that I acquired from biological images is changing over time. So spatial map meaning going back to these pictures, right? So where is the high density, right, in terms of space, and how is that changing over time? So that will somehow be incorporated in our state, okay, of this problem that I'm going to formulate. And in the tutorial, at least, except my last slide in the tutorial, everywhere I'm going to assume that I am actually getting an image before every treatment session, okay? And that's essentially just so that my notation becomes simpler, okay? I can actually generalize this by saying that I take an image at every K sessions, or I don't have to decide beforehand when I'm going to take an image. I can come up with more general problems where that itself is a decision variable and so on. So I can make this really sophisticated in terms of modeling at least. But right now I'm just going to assume that I take an image every treatment session, just so that the notation is easy. Of course, there is a big issue here, meaning that this is going to have economic implications, right? Because the images are expensive, inconvenience, right, for the patient, right? Taking an image every time the patient comes, essentially, and other clinical complications as well, right? So from a practical viewpoint, this is a big assumption, but today I'm going to make that in terms of the math notation, okay? At the end, I'll show you a picture which tells you what is the effect of not taking an image in every session. So I'm going to actually show you a picture of how much you're losing out by not taking images in every session, okay? And that's how I'm going to basically close the talk later on. And as you can imagine, the control variables in the problem that I'm going to formulate will be the beamlet intensities, right? So the U's will be my control variables. And the objective is actually going to be some quantitative measure of treatment efficacy. So I do this dynamic treatment. So how good is this treatment? So I need some quantitative measure of that. So I'm going to actually have that in my objective. So that's the high level framework. So let's start getting into notation and writing down some problems or models. So T, I'm going to call that as the number of treatment sessions. We actually have a follow-on paper that we are working on where we don't even fix this T beforehand, but we actually formulate an optimal stopping variation of this problem where I stop treatment when I think it is okay to stop treatment, okay? But right now I'm going to assume that I'm fixing capital T, and then I'm going to have xt as my state at the beginning of the Tth treatment session. And I think almost all my formulations, the state will have two major components, xt tau for the tumor information and xt phi for the OAR information. Okay, so it will have those two major components, but you'll see that this will actually be a long vector, and we'll talk about that when we get there. St is just the set of all possible states. That's not that important. This notation is, by the way, standard for writing stochastic control problems. If you look at Bertsekas's book in 2007, Dynamic Programming and Optimal Control, this is exactly the notation in this book for writing any general stochastic control problem. I'm just putting this in the context of radiation therapy by calling this as my tumor state, my OAR state, and so on. Okay? So then the K is the same as before, number of beamlets. I will use something called UTXT, which is going to be the set of feasible intensities in state XT. And I will show you later on in my models that what is feasible given a particular state depends on that state. Okay, that's why I'm using this notation UTXT for the set of feasible intensities. And therefore my UT, which is my intensity vector, is going to belong to that. Okay, that set. So that's going to be my control variables. And then I will need, as you can imagine, some kind of a stochastic state dynamics, right? So given a state right now, and given a treatment, right? So given an intensity vector, what will my next state be. So I will need something that tells me that. And then I'm going to have some uncertainty. So this is again standard notation in stochastic control in Bertsekas's book. This theta is going to be my noise vector or uncertainty vector basically. And the standard assumption in Bertsekas's book, for instance, is that this theta t can depend or may depend on xt and ut, but not on old values of the noise. Okay, and that gives you basically a nice, if you will, Markovian formulation. And then I believe most of you are from OR. So as you know, if you have a stochastic dynamic program or stochastic control problem, you will need to find out optimal policies. Okay, so optimal policy meaning it is a mapping from states to decisions, right? Meaning given a state, let's say xt, pi t xt will be the decision that I'm going to choose in that state. Okay, so that's an optimal policy. So the set of all possible policies will be pi. And then the typical way to think about this in stochastic control, again in Bertsekas's book, is to have some kind of an intermediate reward function, meaning that if I choose intensity u in state xt and if the noise is theta t, then this is the reward that I will collect in that period, right, in the stochastic control or stochastic DP language, but in this case in that treatment session. And when this whole thing is over, I'm going to collect a terminal reward, right? So when the treatment sessions are done, so treatment course is done, I will collect a terminal reward, and that's going to be the notation for that. Okay. So is the notation at least roughly clear at a high level? Okay, so this is very abstract, right? I have not told you anything about what these things are. This will become more concrete as we go. But I'll need one more piece of notation. So if I start out in state x1, so at the beginning of the first treatment session, if the state or the condition of the patient is x1, and if I choose to implement policy pi, okay, throughout my treatment course, what does that mean? Policy pi will tell me what to do if I find my patient to be any particular state in any treatment session. Okay, so if I choose to use that policy pi, this j pi of x1 is going to be the total expected reward that I will get over this treatment course. Okay, so that's my notation. And then using this notation, you know, this is the standard stochastic control formulation that you can write. So let me just quickly show you that. So j pi x1, as you can see, is basically the expected reward over the entire treatment course. So all I'm doing there is I'm adding the reward that I collect over all treatment sessions, right? The intermediate rewards, t equal to 1 to capital T, and then I'm adding the terminal reward, right, on top of that. The expectation, right? So this state, right? So the state evolves stochastically, right? So the expectation is with respect to how that state is going to evolve, basically. Okay. So that's j pi x1, and what I want to figure out is basically the largest reward I can get, given that I'm starting in x1, and the notation for that is j star of x1. So that's the largest reward I can get, and that is simply the largest of this objective, which is that expected value, right? It is the largest among all j pi x1s, right? So I want to find a policy that maximizes that subject to this dynamics, okay? Because this is how my state is going to evolve. So this is, of course, very abstract. You know, this is not even talking about radiation therapy really. This is literally copying almost what Bertsekas has in his book, right, on this slide. But I need to give you a concrete special case from radiation therapy, and what I mean by concrete special case is I need to, at least for us to write down a model, I need to give you what my states are for the OAR and the tumor. I need to explain what this set UTXT that I showed you, so what the set of feasible decisions is, and I need to talk about reward functions. So if I give you concrete examples or special cases of these, then that will be our stochastic control formulation of this radiation therapy problem. Okay. So the next 25 minutes roughly, I'm going to give you a special case for each of these. So I'm going to start with OAR dynamics. Okay, and by no means am I saying that this is the only way to do it, right? As you can see, my general stochastic control formulation, and that's in our paper, it is extremely general. Okay, I have not said anything about what those things are. So for example, your hypoxia that you talked about last time can be a special case of that, and we talk about that in the paper as well. But today I'm going to give you one way of doing it. Okay, my hope is that once people start reading the paper, hopefully people will come up with different ways of modeling this, and perhaps there will be special cases or variations of that high-level stochastic control formulation. Okay, so let's start one by one. So OAR dynamics. So the difficulty in coming up with OAR dynamics is the following. Suppose I give some dose to my OAR, so the OAR receives some dose. The effect of that dose on the OAR is not additive over treatment sessions. Okay, and that's in that book. What does that mean? That means 2 plus 3 is not equal to 1 plus 4. Okay, so what does that mean? That means, simply speaking, that if I give a dose of 2 in the first treatment session and dose of 3 in the second treatment session to my OAR, the damage that these two doses do to my OAR is not the same as the damage 1 and 4 will do to my OAR. Okay, and as you can imagine, that comes from the fact that remember a while ago I showed you that curve, that is a nonlinear curve, right? So the doses are not quite additive on that curve. Basically, that's the basic reason for that. In other words, typically, so the difficulty is that the conventional way of treating, as I said, typically is equal dose fractions, right? So I have been using this 2 gray per fraction for 10 fractions, or 1.5 gray per fraction for 15 fractions. Okay, so that is not the same as, let us say, 10 gray in 2 fractions, right? Or it is not the same as 10, 7, 3, right? It adds up to 20, but the effect is not the same, right? And this creates a difficulty, as you can imagine, because I'm not fixing my doses beforehand, right? So I do not know at the beginning how much dose I will give in the first treatment session. I do not know how much dose I will give in the second treatment session, and so on, right? So this is completely, in fact, stochastic and non-stationary, so changes over time. So that's why initially we thought it was kind of difficult to actually come up with appropriate OAR dynamics and what the state should be. And so on. The other complication is that when somebody says that this particular organ at risk, so let us say the spinal cord, can tolerate 45 gray of dose. Okay? Typically, I believe they have some kind of a fractionation scheme in their mind. Meaning, so for example, let's take an even number, so let's take 44, right? They have something in their mind which says that it can tolerate 44 if given in 22 fractions of 2 gray each, right? They don't say it, but I think it is implicit, okay? Or another example, when they say it can tolerate 20, they mean if given in 2 gray per fraction 10 times, okay? So we cannot really directly use that number 44, right? Because I'm not going to give the same dose in every fraction. In fact, I don't know what I'm going to do. It might be completely all over the place, right? Changing non-stationary over time. So that was another difficulty. So we could not use those kinds of numbers directly. Okay. So we wanted to come up with or use a quantitative way to tell whether a dynamic treatment scheme can in fact be tolerated by an OAR. Okay. So that was the challenge, and I believe there might be different ways of doing it. In fact, I think you talked about one related issue in your talk yesterday, and I asked you a question at that time. Okay, so that might be one way of doing it. We are doing it in a slightly different way, so we can talk about that later on again. But I'm going to show you one way of doing this, and we actually used something called biologically effective dose for doing this. And this biologically effective dose idea is in that Bible on radiobiology, if you want to refer to that later. But the idea is pretty simple. So I'm going to actually in 2 to 3 minutes quickly derive things that relate to biologically effective dose. So I'm going to start at the well-known log linear quadratic model of OAR cell kill. It's from that book. And basically it says that the fraction of OAR cells that survive one treatment session with dose D is that. Okay, so it's log linear quadratic because if I take the log of this, I get a linear quadratic function. Okay, where alpha and beta are parameters that depend on OAR. So spinal cord will have different alpha betas found empirically, let us say, right? as compared to some other normal tissue organoids and so on. Okay, so this is actually what I was trying to show you a while ago in that nonlinear curve that I showed you. Basically, it was this fractional cell survivor curve that I was trying to show you. Okay, so from that, using the property of the exponential function, that if you multiply exponential functions, you can add the exponents, right? So that's the property I'm using here. So if I actually give d1, d2, d3, dot, 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 up to dt, okay, the fraction that will survive will actually be a product of exponential functions with d1, d2, and so on, right, like that in the exponent. And I multiply the whole thing, I will actually get sums. Make sense? So exponential a times exponential b is exponential a plus b. That's what I'm using to come here. Yeah.
I guess it says explicitly. You're assuming they're like separated sufficiently in time.
Yes.
Okay.
That's always assumed in the sense that, right, 8 to 12 hour
Okay.
separations that I mentioned. Yeah. So that I think is clear. That's just algebra. So if you look at this, you know, this term lies in that exponent, but basically this expression is what decides how much damage will be done to my OAR, essentially, according to this model. Okay. So if you just stare at this, the units of this are actually not in dose, okay, because this is in the exponent. So this is a unitless quantity, right? So this is actually unitless. The unit of alpha is dose inverse, so gray inverse. So I'm going to just convert this to units of dose by dividing the whole thing by alpha, okay, and that gives me biologically effective dose, okay, and that's the definition basically on my second slide. So the biologically effective dose of d1, d2, dot, 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 dt is simply that term that I showed you divided by alpha, okay, and I got that alpha over beta in the denominator because that alpha vanished, divided by alpha, and I then moved that to the denominator, okay. So that's how I get this PED expression. And that's the definition of PED. Okay. The funny thing is that, if I'm not wrong, this derivation is not in the book. I might be wrong, I don't remember. But there are other ways of thinking about this perhaps, but this derivation is in my tutorial. Okay, so this is how I think of biologically effective dose. I'm not sure this is the exact derivation, but the formula is the same, okay, in the book as well. The beautiful thing about this is that now I can actually kind of start thinking about using this as my state for my OAR, because that relates to, as I said, the damage that I have done to my OAR by giving this sequence of d1, d2, dt up to dt, right? They don't have to be constant or anything like that. That's one. If you stare at this, you will see that this will actually give you a very simple state update formula for the state, right? And that's my next slide, and that's also a beauty of this, I think. So we were very happy when we just kind of discovered this, you know, the fact that, okay, this gives me a very simple PED update formula, meaning that if I give a sequence from d1 to dt plus 1, then using that formula I have this, right, this, and because this is all just additive stuff, right, I separate the terms and I get PED up to t plus the additional damage that I do in that session. Make sense? So that's the beauty of this. So I'm actually going to use this as the state for my OAR. And going back to that X notation for the state. So all I need to do is, now I have an equation that tells me how my OAR state is going to evolve. This is my BED after like T, which is here. This is my next BED, and I simply need to add a dose term plus a scaled squared dose term, right? And as you remember, this is the dose that is given to the jth voxel of the OAR, right, in our notation. And this is the square of that divided by alpha over beta, right? So I now have a simple state update formula for my OAR in terms of my current state and the intensity vector that I choose in that treatment session, right? That's what I need, and that's what I have now. One more last piece. Initial BED is 0, assuming that I have not given any treatment before that. So that BED is just 0, that's fine. Or any other number, doesn't matter. Just I need some initial condition. So now I have OAR dynamics. That also gives me another very elegant thing which I like. And that is, it actually is going to give me the set of feasible controls. Okay? So what we did is that, remember I had mentioned that it is difficult meaning it's not obvious how to compare two different schemes, right? So 2 gray per fraction 10 times. Is that the same as 3145 to 3145 or something like that? If I want to compare two crazy things like that, how do I compare? And how do I say whether this thing is even feasible, whether the OER can tolerate this crazy thing, right? And the idea is that here, so I'm going to assume that some sequence D1 to D2T can actually be tolerated if its BED is less than the conventional BED. Okay, so let's go to conventional BED. So conventional, remember, constant. So C gray per fraction for n sessions. Suppose that is the constant per session, and that is known. It is known that OER can tolerate that. So I simply compute its BED, and the BED is simply the sum of the doses. So I'm giving C n times, so that's the sum, and then C squared n times divided by alpha over beta. So this is the BED of the conventional treatment fractionation scheme, which the OER is known to tolerate. And what I am saying here is that some other sequence D1 through DT will be tolerated if its BED is less than what the OER is known to tolerate. And why is that an appropriate assumption? Because the BED essentially characterizes damage to the OER, right? So if this damage was okay, then this must also be okay because the damage is in fact less. Okay, that's the idea. And as you can see, this will give me the set of feasible controls. Why? Because I have my BED in terms of my U, right? So that's my next slide. So given that I am in state xt, right? As I said in the previous slide, this is my BED, right? New BED, and then that has to be less than this, and that gives me the set of feasible U's, right? So this way of modeling not only gives me my OER dynamics, but also gives me the set of feasible U's. So let me speed up a little bit. So the next part is tumor dynamics. So what we did was tumor dynamics, we also used a similar model. The only difference was that, so there are papers out there which says that the alpha over beta ratio for tumors is different from typically the alpha over beta ratio for the OARs. In fact, so the alpha over beta ratio is high for these tumors. So I'm actually ignoring the quadratic term here. You don't have to do that, we don't have to do that. In fact, we have follow-on models where we actually did not do that. There are a lot of different ways in which you can model uncertainty in tumor response. This is one example of doing that. So all I'm doing is I'm using a similar log linear model here instead of log linear quadratic. The only difference is that I'm going to model this parameter as a random variable, right? To model uncertainty in tumor response instead of using a constant, okay? That's one way of doing it. In my NSF grant, in the proposal, I have talked about different possible ways of doing that. This is one way of doing that. In the tutorial, I have assumed, in the tutorial chapter, I have assumed that these are, so the thetas, so these multipliers here are independent across T and I, not necessarily identically distributed, just independent. I have other models in my proposal, for instance, where I've relaxed that assumption. That assumption should be relaxed if you are learning these things over time. Okay, there will be some kind of dependencies if you are learning your new distributions based on what you have seen and so on. When might these be independent? If you are thinking about something like this theta, so T comma I is treatment session T, tumor voxel I, is some constant times some stochastic noise. Right? That's one way of doing it, or some constant plus some stochastic noise. And in stochastic control, it's common to assume that those kinds of noise terms are independent, for instance. Okay, so that's the setting under which this assumption will be okay, or at least typical or standard from a stochastic control viewpoint. And then the last piece I need to tell you is treatment